let's work some problems using some explicitly given sequences. What we want to do is we want to write the first 5 terms of these sequences. So what we're really doing now is just getting familiar with them. Our first is a sub n is, in the nth term of this sequence, is negative 5 over 6 to the n. So what we have to do when we're writing these sequences is say, all right, I need a1, a2, a3, a4, and a5. So in the first case, what we're going to do is we're just going to set, what we want to do actually is just match these letters. That's actually what we're trying to do. So match those letters. When n is 1 here, it's 1 here. So negative 5 over 6 to the first power is negative 5 over 6. Simple enough. Now in the second term, again, we're matching those letters, so we're plugging in. We're saying negative 5 over 6 to the second power. And so that's positive 25 over 36, right? Because the negatives cancel because we're squaring them. In the third term, we're going to do the same thing. We're going to replace n with 3. So, whoops, I need a negative here. Negative 125 over 216. So one thing you may be noticing is that in this particular case, I'm just multiplying by another negative 5 over 6. So over here I get negative 5 over 6 to the fourth. So I get 625 over 1296. And then finally I get negative 5 over 6 to the fifth, which is negative 3125. Ooh, that's a little tough for me to do in my head. 7200, 540, so 7740 plus 36, 7776. I think that's right, I don't know. Hey, it is. Congratulations to me. So that's the idea here. You just multiply that out. Just getting familiar here. This one's an interesting sequence. Bn is cosine of n pi over 2. So I do b1, b2, b3, b4, b5. So again, all we're doing is matching letters. So these n's match. So when we're dealing with the first term, n is 1, so that's cosine of pi over 2. Well, that's 0. The next one is cosine of, so we have a 2 here, so it's 2 pi over 2, which is the same thing as cosine of pi, so we get negative 1. B3 is cosine of 3 pi over 2. Well, that's 0. Over here we have cosine of 4 pi over 2. Now, 4 pi over 2 is just 2 pi, right? And cosine of 2 pi is the same as cosine of 0, which is 1. And then we have cosine, so for the fifth term we have 5 pi over 2. So cosine of 5 pi over 2, if you spin that around the unit circle, if you start at 0, it's pi over 2, pi, 3 pi over 2, 4 pi over 2. So when we go up to 5 pi over 2, that's the same as cosine pi over 2, which is 0. So what you see on this one is it's going to alternate. It's going to keep going around. It's going to go 0, pi, or it's going to go 1, 0, negative 1, 0, 1, 0, negative 1, 0, 1, 0. Right, I'm sorry, it's this 4 sequence. 0, 1, 0, 1, 0. The next term would be negative 1. Try that out yourself and see. So what you find is there are certain sequences that are periodic, as they say. They repeat. Just like the cosine function repeats, this sequence will also repeat. Alright, so let's keep on going. I have Cn is 15 plus 2 over n minus 5 over n squared. This is done the exact same way, so we don't have to really overthink it. So in the first term, I plug in 1 for each of those. So that reduces to 12. Hopefully that arithmetic isn't bothersome. Now this one's going to be a little trickier. We have 15 plus 2 over 2 minus 5 over 2 squared. So that's 15 plus 1 minus 5 fourths. That can't be right. I think that is right. Yeah, 59 fourths. The next one, we keep going. It's 15 plus 2 over 3 minus 5 over 3 squared. 15 plus 2 thirds minus 5 ninths. So in this particular case, what it would be helpful to do is get a common denominator. So a common denominator is 9, so that'll be 135. Right, we have 135, and this will be 6 over 9 minus 5, so that'll be 136 over 9. Our next one is over 4. This is 4, so we have 2 over 4 minus 5 over 4 squared, which is 15 plus a half minus 25 over 16. So we got to get a common denominator again of 16. So that'll be 240 plus 8 minus 25 for 16, or 223 over 16. And finally, when we have 5 here, it's 15 plus 2 over 5 minus 5 squared. So luckily the 5's cancel. We get a common denominator of 5. So 75 plus 2 minus 1, 5. So we get 76 fifths. So, it's not readily apparent what the pattern from this is, but if you looked at this and you took n out to infinity, for instance, what you would find is both of those would vanish. So this sum actually approaches 15. But if you were to plot these points on a graph, what you'd see is this is 12, this is almost 15, this is just a hair bigger than 15. So this is a hair smaller than 15, a hair bigger than 15. This is a little under 15, this is a little over 15. So you're probably going to see it kind of wobble and then eventually move to 15. And finally, we have a recursive sequence. So we need to figure out how to do this based on the recursion formula. So I have D1. And I have to use this recursion formula. So the recursion formula says, for each term, take the previous term and square it, then divide the result by 3. So I have to take the previous term. So let's write this out a little more explicitly. D2 would be D1 squared over 3. D3 would be D2 squared over 3. D4 would be D3 squared over 3. And D5 would be D4 squared over 3. So then I can start plugging in. I say, okay, well D1 is 6, so 6 squared over 3. Well, that's 12. Okay. So then I say, okay, well I need to square D2, so I have to square this term, which is 12 squared over 3. So what's that, 48? So that becomes 48. Then I have to do 48 squared over 3. And and frankly, I don't know what 48 squared is. But this is going to be 48 times 16, which is 800 minus 32, so that'll be 768. And then finally, I have to say, all right, this is 768 squared over 3, which, ugh, right? That's 768 times, so 768 divided by 3 would be 256. And I don't know what 768 times 256 is. It's a big number. I know that much. So I'm going to stop there. You can plug that in a calculator and find out. But the idea here for recursive sequence is you're just using the previous terms. And what makes this annoying, right, is because I have to compute each. I couldn't start at D5. I have to go to D4 or D3. Up here I could have started at C5. I don't need to know anything about these previous terms, but for the recursive sequence I do. So recursive sequences are not super nice to deal with. That's why we don't like them.